Here's my tutorial on weighted average mass. So if we had a value that was 28, for instance, grams per mole, or whatever, and a value that was 30 grams per mole, or whatever, and we said, what's the average? It would depend on the percent that each one was of the total. Maybe this is 20% and this is 80%. Maybe this is 10%, this is 90%. Now, in 7th grade kind of averages, they assume that they are worth the same. In other words, they assume that they were worth 50% each when they teach averages to little kids, 6th grade and so forth. And then you add them together and you divide by 2. That assumes that they are worth 50% each. They're equally valuable, or they occur equally as often, which is the point here. So let's pretend we have an isotope that is 28 grams per mole and an isotope that is 30 grams per mole. But they occur in equal amounts, so they're 50% each. Then, of course, a lot of people leap immediately to, well, the average then is dead between them. It's 29. And that's true. But watch, I can also get the answer this way. Let's multiply by the percentage that it occurs in, 0.5, not times 50. This is 50% in regular numbers, 0.5. And I get 14. 30 times 50%, which is 0.5, is 15. And if I add them together, I get 29. So that's how we're going to get the weighted average mass when these aren't equally distributed. So here's an example of masses when they aren't equally distributed. Let's take a short time out and talk about AMU, which is atomic mass unit. Now, maybe I've said this before, but here's what happened when people wanted to talk about the mass of atoms. It's incredibly small. And so what they basically did was they just said carbon 12 will be 12 atomic mass units, 12 atomic mass thingies, because we said so. Because you got to start somewhere. Atomic mass units. And then a mole is the number of these you got to count, you got to group together such that you have 12 grams. So when they say AMU, it is also the grams per mole, because a mole is defined as the number of atoms or molecules that will turn the AMU into grams. So when I put AMU here, it is also interpretable as grams per mole. Notice my answer is both. It is either one. So if we have this pretend lead, we won't get the true answer here. I just faked the numbers because I wanted to see if people were getting the right answers and not just looking it up. So in number 1 here, we have a mass of 82 plus 122, because that's the parts that matters, the protons and the neutrons, which makes 204. We will multiply by the percentage here as a real number, not times 39, but times 0.39, because that is the real number version of 39%. And we get 79.6 AMU. We'll do that again. Add these up, 206 times 0.2926. Getting this, do it again, and we will add up these answers, and this would be 205.0, the grams per mole of the overall average mass. This would be the number that you would print in your periodic table as long as these facts are all true. It would say 205.0 in the box for lead on the periodic table. This is the weighted average mass, taking into account that these percentages of abundance do not match each other. It is not 25% each. We had to compensate for the different percentages. So then 2 and 3 are basically the same thing. Just practice on those. For honors, I decided maybe we don't need all this practice, so I have skipped ahead. There is another version of this kind of problem. If you know the weighted average mass, and I had to change this one because I realized I'd given myself an impossible answer, then you can determine the abundance, the percentages that they occur in. There is one trick. You have to have only 2 isotopes. So we will pretend there are 2 isotopes. If you have 3 or more isotopes, you have more than one unknown, and you get into, I guess, a series of equations or something. And honestly, it's been too long since my Algebra 2 class that some of you in and so forth. And I mean, I'm sure I could understand it if somebody showed it to me, but I refused to take the time to work it up. So we're going to pretend that there are two isotopes. So fake element W, I know there's a real element W, ignore that, has 15 protons, and then we have two isotopes. So we have W27 mass version and W28 mass version. Now here's the logic. This could be 10%, which would mean this would be 90%. This could be 15%, in which case this is 85%. In other words, it's 100% minus whatever the other one was. Or in regular numbers, it's 1, because 100% is one whole. It's 1 minus whatever you just said. If this is 90%, that's 0.9. And then this is 1 minus 0.9, which is 0.1, or 10%. If this is 0.3 or 30%, then this one is 1 minus the 0.3 is 0.7, 70%. So I'm going to assign an X percentage to whichever one. I just chose this one because I wrote it first, honestly. And this percentage that I'm going to multiply by will be 100% or 1. Don't write 100%. It screws it up. 1 minus whatever that one is. If this one's 0.1, this one is 0.9. If this is 0.2, this one is 0.98. But we don't know what it is. Then we can just expand this and solve. And this is 27x. Multiply in here is 28. Multiply in here is minus 28x. This minus that is minus x. This subtracted over is negative 0.6. The negatives cancel out, and x is 0.6 or 60%. What is x? It's the percentage, essentially, that I assigned to 27. It doesn't matter which one you pick. You're going to get the same answers. If you solve for this one, you would have gotten 0.4. If you assigned x to this one, you'll get 0.4, and then this will be 0.6. You'll get the same answers either way. So the negatives cancel out, and I get, because x goes with W27, 60%, which is 0.6, for the 27 mass version. And that means that 40% goes with the other one.